Okay, I'm audible, no? Hello?
Yes, sir.
Yes, sir.
Okay. Let's discuss about the question and answers of oxidation. I think you are aware about the second semester molecular sieves. Okay, so in that you learned about the role of crown ethers in oxidation. So more particularly, the K-menophore is not soluble in benzene, but when you are using a crown ether as a solvent, so the K-menophore is soluble. Okay, so what will happen? More particularly, what is the question? What is the function of crown ether in K-menophore oxidation? So this is more particularly related to the molecular sieves previous semester one, but it is related to the oxidation. That is the reason 2 marks question is asked. So crown ethers are used to increase the salt solubility. Okay, crown ethers are used. I think you are aware about the host guest phenomena. Okay, here the host is 18 crown 6, whereas the guest is K-menophore. So when there is a host guest interaction, so this concept is useful for the oxidation of K-menophore even in the organic solvents. Okay, that is the advantage about the use of crown ether in organic synthesis. Let's give an entry. Right. Okay. Right. So what you need to do, crown ethers are used to increase the salt solubility and also increased anion reactivity in organic synthesis. So for example, KMnO4 can be soluble in benzene by complexing with the dicyclo 18 crown 6. Okay, to provide the convenient and efficient oxidant. So this answer you can write it for the above question. The question is, what is the function of crown ether in KMnO4 oxidation? And the next question, predict the product and propose the mechanism. So this is the cyclohexanol and a sodium dichromate. I think you were more particularly in presence of H plus. So H plus means what it will do. Initially, a primary alcohol is converted into aldehyde. Later, aldehyde also further converted into acid. So that is the answer here. So let's make an entry. Right. Okay. So cyclohexyl alcohol. Okay. Cyclohexyl carbinol. Okay. This is called carbinol. Converted into cyclohexyl carboxylic acid when it is treated with sodium dichromate in presence of H plus. And cyclobutene when it is treated with osmium tetroxide, it converts a double bond into cis diol. And next question, formulate a product and propose a suitable mechanism. So this is the reaction. The acetone, a ketone it is treated with potassium dichromate in presence of dilute sulfuric acid. So what will happen? Initially, a ketone, what will happen? This anion part will attack here, and this can go here. Okay, let's not talk about mechanism, but you can write the mechanism for the conversion of a ketone, more particularly acetone, into two fragments. So that means this carbon is converted into carboxylic acid, and this carbon is converted to carboxylic acid, and there will be a breakage here. Okay, so acetic acid and formic acid are the products obtained when acetone is oxidized with potassium dichromate. So then predict the product and propose a mechanism. So here what will happen? A double bond. Okay, a double bond or olefin or alkene, when it is treated with KMnO4, more particularly in alkaline media, it will convert a alkene into cis diol versus 1,2-diol. And here I am also mentioned the mechanism. So this anion can form a bond with this carbon, and this bond pair is going over here, and there will be a new bond formation between this carbon and this oxygen. A cyclic uh, uh, cyclic chromate was manganate was formed, and then breakage. How the breakage? This bond pair can come over here, and this bond pair will sit on manganese, thereby manganese reduces. So that is how cis diol is obtained. So, and one more question, give the products formed with of the following. So in it's what is called as chromium trioxide in presence of H plus. H plus means Jones reagent. So what will happen? A secondary alcohol is converted into ketone. So KMnO4 means this does not react with alcohol, but it will react with a double bond, more particularly in alkaline media. pH more than 7 means it's alkaline media. It converts a double bond into cis-diol. Then osmium tetroxide. So more particularly stereochemistry. Discuss the stereochemical similarities in oxidation of alkenes by osmium tetroxide. So here osmium tetroxide is, I think you are aware that osmium tetroxide is a costly reagent, but it can be used in a catalytic amount in presence of co-oxidizing agents such as N-methyl morpholine. So this one is the N-methyl morpholine. It's a co-oxidant. What is its role? It converts osmic oxide into osmium tetroxide. Osmium tetroxide is responsible for the conversion of an alkene, okay, an alkene into cis 1,2-diol. Okay, so how it is reacting? It's a mechanism is here. There will be a new bond formation between this oxygen and this carbon, and this bond pair will form a new bond with this oxygen, and this bond pair reduces the osmium, and cyclic osmate is the intermediate, and cyclic osmate is attacked by water molecule, and there will be a cleavage of one of the osmium and oxygen bond. So that is how intermediate is obtained. Later on, a water lone pair present on the water again attacks an osmium, and there will be a bond formation. This bond picks up a proton and convert it into cis-1,2 diol. This is the mechanism. This is the reaction. So this, what is the stereochemistry here? The stereochemistry here is a formation of cis-1,2 diol. Okay, that is the stereochemistry. Then we'll go to the next question. So predict the product and suggest a suitable mechanism. So here what you can observe is again a Jones reagent, but Jones reagent it's fine, but hydroxy group is a tertiary alcohol. So tertiary alcohol resist oxidation, but there will be a loss of proton. Okay, loss of proton means proton here loss and forming an alkene is the product. Of course, if you are using a excess amount of chromium trioxide, what will happen? The obtained double bond can react. No, this is not a KMNO4. No, if it is a KMNO4 or if it is a dichromate, okay, then there will be a reaction with double bond. But since it is acidic condition, double bond is the product. So then what is the product of the following reaction? Propose a mechanism. So here an aldehyde, when it is treated with KMNO4, more particularly here H plus condition, acidified potassium permanganate. So you acidified, what will happen? An aldehyde is converted into carboxylic acid, RCOOH. Aldehyde is converted into carboxyl. If you are looking into the mechanism, initially there will be a lone pair present at the oxygen can obstruct a proton, forming a intermediate. At this intermediate, potassium permanganate will react here, forms an intermediate like this. Then the bond pair, okay, alpha proton is going out, the bond pair is coming over, this will go out. So that is how the aldehyde is converted into carboxylic acid. So now let's look how is the following conversion affected. Propose a mechanism. What you can observe here, this is called alpha proton or alpha carbon. What is happening here? A alpha carbon is converted into ketone. Methylene is converted into ketone. So here you need to apply the selenium dioxide. Selenium dioxide, it converts a acidic proton, okay, methylene proton or methyl proton into a oxidized form. So you know that this what you call maybe up to this is called benzyl phenyl ketone. So benzyl phenyl ketone, it will be in the keto-enol tautomerism. This is the keto form and this will be the enol form. Afterwards, what will happen? There will be a new bond formation between this bond and this selenium. Okay, so it will form an intermediate like this. At this moment, there will be a new bond formation between this carbon and this oxygen, and this bond pair is going over here, and this bond pair is breaks. So that is how a ketone and O-selene hydroxy group is obtained, and water present in the reaction can obstruct this proton, and this bond pair is coming over here, and OH is going out, water is leaving group. And of benzyl phenyl ketone into a benzil. Name of this compound is called benzil. Okay, right. This is again useful reaction because benzil formation means it's useful because benzil can be converted into benzylic acid. So then I will go to the next question. It's a general question. You can write with a suitable mechanism, describe the reactions of lead tetraacetate with vicinal diols. Vicinal diols means maybe a cleavage, glycosidic cleavage that you need to write. Olefins vicinal diol. Okay, olefins compare with paroidic acid. Right. So this also a general question. You can just look into that. And if you want to know about more about oxidation reagents, maybe you can also look into the organic synthesis by Smith. Okay, that book you can follow it. Okay, that is framed as per the syllabus. Then here I am taking a glycol 1,2-diol. When it is treated with lead tetraacetate, it will form an acyclic intermediate, and there will be a cleavage here forming a 2-carbonyl compound. Similarly, what is called as paroidic acid, it will also react with the diol. How the diol is obtained? How the diol is obtained? You know that maybe an alkane is treated with KMNO4, it will give you diol. Osmium tetroxide, that also will give you a alkane into 1,2-diol. So then the lone pair present on this oxygen can attack here, and this can go out, an intermediate formed like this. And the lone pair attack here, and this can go out, a form cyclic iodinate intermediate. And there will be a cleavage. This bond pair can come over here, this can come over here, this bond pair can come over here, can leads to a 2 dicarbonyl compounds. And next question, it's about actually what you need to do. Here there won't be a methyl group. Okay, complete the following reaction and outline its mechanism. This is the product only, but this product follows a free radical mechanism that lead tetraacetate, it can give you lead diacetate and forms an acetate radical. This acetate radical undergoes homolytic cleavage here, and methyl radical is obtained and carbon dioxide is going out. The obtained methyl radical, what it will do? So it can obstruct here this particular bond pair can undergo homolytic cleavage, forms a methyl radical bond formation. Then this proton undergoes homolytic cleavage, so giving rise to the product called trinitrophenol. Okay, trinitrophenol means TNT. And of course, this is a termination reaction. Acetyl radical can react with hydrogen radical, forming a neutral product called acetic acid. Then suggest a suitable mechanism for the following. What is this? Again, here this question is based on the allylic proton. This is a allylic proton. This allylic proton is converted into hydroxy. How it is converted, and here is the mechanism. So what will happen here? Okay. Allylic proton means this proton. So this proton, you know that this proton is acidic. There will be a new bond formation between this bond pair and this selenium. That's what I have written here. And this can pick up a proton. The proton may be this one. And later on, what will happen? This bond pair can form a bond with this carbon, and this bond pair can move over here, and this bond pair will sit on selenium. That is how an intermediate is obtained. Now the water is attacking to the selenium, converts selenium into selenium metal. Okay, it's about selenium oxidation of conversion of allylic proton into hydroxy compounds. I think you know what is desmartin. Desmartin is a hypervalent iodine molecule. This compound is called desmartin reagent. So what is the role of desmartin reagent? It will convert a primary alcohol or secondary alcohol into ketone. So what is the specialty about desmartin? Desmartin oxidizes the primary or secondary in presence of other oxidizable oxidizable functional group present in a substrate. So if you're looking into the mechanism, the lone pair is attacking here and O acetate will go out. And here there is an intermediate is formed in such a way that there will be a intramolecular transformation. How the transformation? The bond between the iodine and acetate, this bond is going out, and this bond pair is sitting on the iodine, and there will be a new bond formation between the oxygen and proton, and this bond pair is coming over here. That is how a secondary alcohol is converted into ketone, and this is the byproduct. Swaran oxidation means it's where there is a involvement of DMSO. DMSO converted into dimethyl sulfide. And here there will be a oxalyl chloride and triethylamine base. So what is happening here? So here there will be a conversion of primary alcohol into aldehyde, secondary alcohol into ketone. So here there will be involvement of DMSO. So how there initially there will be a reaction between the DMSO and oxalyl chloride. How the reaction? The bond pair can attack here and the chlorine will go out. So that is how an intermediate is formed like this. At this moment, the outgoing Cl can again attack S plus, means thionium ion. So what will happen? It will form a dimethyl thionyl chloride. It's not thionyl chloride, sulfur chloride, and this dimethyl sulfur chloride is attacked by a primary amine. Okay, the lone pair is attacking here, and an intermediate is formed like this. At this moment, this bond pair is this proton is captured by triethylamine. Triethylamine is a base, and this bond pair is coming over here. Okay, otherwise what it can do, it can also picks up a proton present here. Okay, that is shown in the second step. Okay, initially there will be this triethylamine capture proton and forms an anion. So the obtained anion capture the proton from here, alpha hydrogen, and giving rise to aldehyde as the product. So I think here itself I am explained about what is Desmartin. So again one question is there on the Desmartin. Desmartin oxidation reagent is a hypervalent iodine compound. It converts a primary or secondary alcohol into carbonyl compounds. I think this question I have given. What it will do? Here CHO, here CHO. So there will be a breakage here. This is one CHO. This is one CHO is the product. And Baeyer-Villiger oxidation. What is Baeyer-Villiger oxidizing agent? Metachloroperbenzoic acid is the Baeyer-Villiger oxidation. So what it will do? It will convert a ketone into esters. Okay. So if the ketone is a cyclic ketone, then lactone is the product. So what is this will be the general reaction. Maybe you can say that a ketone, when it is treated with perbenzoic acid or metaperchlorobenzoic acid, both it will convert a ketone into ester. So if we are looking into the mechanism, this is a perbenzoic acid structure. So in presence of base, it will form an anion like sodium perbenzoate. This anion, and you know that this reaction, what proton is liberated, this proton react with the ketone and forms a carbocation. So at that time, peroxide anion, it will form a bond here, electron deficient one, and it will be this is conveniently written like this. At this moment, okay, this bond pair can come over here, and there will be a migration of one of the R group from first position to second position, means that is the oxygen position. So thereby it leads to the formation of ester, and benzoic acid is a byproduct, it will go out. So these are the two examples. You can observe that cyclohexanone is converted into what you called tropino. It's not tropinone, it is a caprolactam. And acetone is converted into methyl acetate. This is a methyl acetate. And I think you know that this is also a what is called as epoxidation. Metachloroperbenzoic acid means it's an epoxidizing agent. It will act as a source of source of oxygen. Then what will happen? The oxygen will attack a double bond, forming an epoxide. Acetophenone. So identify the product and propose a suitable mechanism in the following. Acetophenone, when it is treated with metachloroperbenzoic acid, you know that acetophenone means C6H5COCH3 is called acetophenone. So when it is treated with perbenzoic acid, it will act as a source of oxygen, and the oxygen is added between the phenyl group and carbonyl group. So that is the thing. That means between the methyl and phenyl, phenyl is migrates, okay, as per the migratory order. So this is the mechanism. So mechanism I have written here. Perbenzoic acid, it will be in equilibrium with perbenzoate and proton. The obtained proton forms a bond with the oxygen of the acetophenone. It will form an intermediate, and this anion will form a bond with this electron deficient carbon, and it will form an intermediate like this. At this moment, this bond pair can come over here, and this phenyl group is moved from this carbon to this oxygen, and this bond pair is going out and forming a carboxylic acid. This part is carboxylic acid, and this part is called ester. So this is how the acetophenone is converted into an ester. Let's give an entry. Okay. Right. Perbenzoic acid. So this is how acetophenone is converted into ester. Right. So next is explain the Sharpless epoxidation. More particularly here in this place, I am in this oxidation state. I am not discussing about the mechanism part, but when I am discussing about the asymmetric synthesis, that means one more unit in this paper. So during that time, I will discuss about the mechanism, because there will be a involvement of complex molecule. I will tell you how the stereospecific epoxides are formed when you are taking a different means what you call a dextrorotatory or levorotatory of diethyl tartarate. So Sharpless epoxidation, you need to remember that it's a conversion of allyl alcohol into epoxy alcohols. So this stereochemistry of the epoxy, it depends upon the plus or minus of diethyl tartarate. Okay, if you are using a minus, you will get the hydroxy means epoxide is towards the observer, and if you are using a plus diethyl tartarate, the epoxide is away from the observer. That's what you need to remember. And here the tertiary butyl hydroperoxide, it will act as a source of proton, and titanium, this is a catalyst. Okay, so maybe I will explain what is how the mechanism maybe the when I am discussing about the asymmetric synthesis. And then okay, so write briefly the preparation, properties and application of trifluoro peracetic acid. So that means here you need to, maybe you can take a trifluoroacetic acid and treat with hydrogen peroxide. You will get a trifluoroperacetic acid. So that's about the preparation. And properties means it will act as a source of proton and a source of oxygen and convert a olefin into epoxide. That is the application. Right. And suggest a method for effecting the following transformation. Here, a 6-membered ketone is converted into 7-membered lactone. So this is also one of the application of peracid. And this is one more question. Show how the lead tetraacetate and peroxidate oxidants are used to cleave the alkene. Maybe this you can look into the textbook called Smith. You will get an answer for this. So tell me, is there any doubt in the question and answers of oxidation? Hello?
No, sir.
Okay. So if there is no questions means I will go for one more chapter called reduction. Is there any questions on oxidation? No questions?
No, sir.
Okay. I will present the what is called as a reduction slide. Okay. Right. Okay. I think now up to this we discussed about oxidation. So maybe now onwards we need to talk about reduction. So what is reduction? Anyone?
Addition of hydrogen.
Of hydrogen.
Addition of hydrogen, addition of electron, and removal of oxygen. So removal of oxygen here, addition of electron here, addition of hydrogen here. So combinedly we call it as a reduction. Okay, so addition of hydrogen, enaldehyde is converted into alcohol. Removal of oxygen, a carbonyl compound is converted into hydrocarbon. And then what is called as addition of electron. So you know that sodium, okay, sodium what it can do, it can give one electron. So where it will give the electron deficient carbonyl carbon, and this bond pair will sit on this oxygen. That is how a radical anion is obtained. So what it will do, this radical anion can undergo dimerization, forms this particular product. And this anion can picks up a proton and forms a pinnacle. Okay, these kind of molecules are called pinnacles. Of course, you can also call it as a glycal compounds. Glycol is the product. So now you know that reduction means addition of hydrogen, removal of oxygen, and addition of electron is called reduction. So now I think you are aware about the complex metal hydrides. So what are complex metal hydrides? A number of metal hydrides have been employed as reducing agents in organic chemistry. but most commonly used are lithium aluminum hydride. So lithium aluminum hydride is also called as LAH. So lithium aluminum hydride belongs to the complex metal hydrides. Similarly, sodium borohydride NaBH4 is called sodium borohydride. This sodium borohydride is also belongs to the complex metal hydrides. So what complex metal hydrides do? So these complex metal hydrides act as a source of hydrate. So hydride means H minus. So what H minus will do? It can add to the electron deficient carbon or electron deficient species. So let's take the first one, what is called as lithium aluminum hydride. LiAlH4 is called lithium aluminum hydride. LiAlH4 is the formula. LAH, sometimes people used to mention as a LAH. LAH stands for lithium aluminum hydride. How one can prepare LAH? So it is possible to prepare LAH just by the reaction of lithium hydride and aluminum trichloride. So reaction of lithium hydride and aluminum trichloride gives lithium aluminum hydride. Lithium aluminum hydride is a complex metal hydride, and it will act as a source of hydride, and it can give 4 hydride molecules to the substrate. And one more thing I need to mention, lithium hydride or sodium hydride or potassium hydride, all these things are hygroscopic in nature. Hygroscopic means if you are exposing to the atmosphere, it can catch fire because it can absorb the moisture present in the atmosphere and it can go inflammable. So that is the reason once the lithium aluminum hydride is obtained, it's a what is called it's a solid one. Lithium aluminum hydride is a solid one, and of course it's also available in the form of lumps. Okay, lumps or tablets, in the form of tablets, big tablets. More particularly a cement colored, a gray colored compound it is. And this lithium aluminum hydride, it can react with the moisture present in the water. So what it means? So it means that uh, you have to do a reaction in such a way that in a inert atmosphere. So inert atmosphere means the reaction flask should be free from the water, should be free from the air. That means you have to create a inert gases such as argon is the best one. Argon you can use to create an inert atmosphere. So in addition to the argon, some people used to use a nitrogen, but nitrogen to some extent it contains moisture. That is the thing you need to remember. So argon is the best one. Then what will happen? Lithium hydride can react with water, forms a lithium hydroxy compound. This is of this is not of our interest. Our interest is lithium aluminum hydride. So what we can say that lithium aluminum hydride, it is possible to prepare starting with the lithium hydride and aluminum chloride, but the obtained one is hygroscopic in nature. So that is the reason whenever we are using lithium aluminum hydride, we should do the reaction in a inert atmosphere. Inert atmosphere means free from water. Why we need to do? Because water itself react with the lithium aluminum hydride and gives rise to unwanted product. Okay, that is the reason we have to go for a inert atmosphere. And one more thing, lithium aluminum hydride, it also react with the ethanol, means alcohol. So what it will give you? It will give you tetraethoxy aluminum lithium is the byproduct. So overall, what we can say that lithium aluminum hydride can be prepared by the reaction of lithium hydride and aluminum chloride, and it should be used in inert atmosphere. But if it is readily react with water as well as ethanol. Otherwise, what we can say that acidic proton. So ethanol, it will act as a source of proton. That is the reason. So this is about a little preparation and properties of the lithium aluminum hydride. So now I will take up this lithium aluminum hydride for the reduction of carbonyl compounds. So I will go to the next one. I am giving heading reduction of carbonyl compound. So you know that carbonyl compound means RCOR is called carbonyl compound. This carbonyl compound, when it is treated with lithium aluminum hydride, as I mentioned that lithium aluminum hydride, it can act as a source of hydride, means H minus. So H minus will add to this carbon. If H minus is attacking here, then this bond pair will pick up proton. So that means a carbonyl compound is converted into alcohols. So if we are looking into the mechanism, so here I mentioned lithium aluminum hydride, it will be in equilibrium with lithium plus and AlH4 minus anion. So then a carbonyl compound, maybe it will act as a source of hydride, I mentioned, no? So AlH4 minus means this hydrogen along with this bonded pair, it will transfer from here to the electron deficient carbon, and this bond pair will form a bond with aluminum. So an intermediate is obtained. So then at this moment, this allyl oxy, means aluminum oxyhydride, it can react with the uh, three molecule of carbonyl compound. Why? Because this aluminum can transfer 3 hydrogen to the 3 carbonyl compound and giving rise to intermediate. Okay. This maybe here small correction you need to make it. This H3 is not there, only aluminum is there. Okay, H3 is not, only aluminum is there. That's what you need to remember. Maybe I will try to correct it now itself. Okay, so now I am removed the H minus, so aluminum is there. So this is the correct one. So it will form a alkoxy. This compound is called alkoxy aluminum. Tetra alkoxy aluminum is an intermediate. This tetra alkoxy aluminum on hydrolysis, more particularly the acidic hydrolysis, there will be a cleavage. Aluminum trihydroxy aluminum is the byproduct, and here there is a cleavage and alcohol is the product. So of course this is the third step one. The lithium can react with hydroxy, forms an lithium hydroxide. Aluminum can react with hydroxy, forms an aluminum hydroxide. So these are the byproduct, and this is the alcohol is the product. This is about the general mechanism of a carbonyl compounds is converted into alcohol. So now I will go to the next slide. So in the next slide, I am explaining about the few examples. So how the a carbonyl compound is reduced. So I am taking examples. So look here, this is one alpha beta unsaturated carbonyl compounds. More particularly, it's called 1, 2, 3, 4. So uh, butenol, 2-butenol is the IUPAC nomenclature. So H minus can add to this carbonyl carbon and giving rise to an alcohol. And one more thing, so if we are doing same reaction at a high temperature, then in such cases this double bond also gets reduced. So here I am giving an example. So lithium aluminum hydride in ether. Ether is a solvent at minus 10 degrees centigrade. Minus 10 means minus. So now presently the temperature may be around 15 to 20 degree temperature. But minus 10 means it's so usually water will be in the ice form. So at that temperature, the lithium aluminum hydride can react with the carbonyl compound, giving rise to alcohol. But if slightly more than the room temperature, so 35 degree means it's more than room temperature. So at that temperature itself, a carbonyl compound is converted into alcohol and double bond is converted into single bond. So that is about the lithium aluminum hydride. That means depends on the temperature. In addition to the carbonyl compound, a double bond is also reduced with the lithium aluminum hydride. So here I am taking one more example, a carbonyl compound, cyclohexanone. This CO is converted into alcohol. This H is obtained from lithium aluminum hydride. So that's what I have shown in all the example. Okay. So the H should be from the lithium aluminum hydride. These are the few examples where there is a alpha beta unsaturated carbonyl compounds are the starting materials. So now I will go to the one more examples. So in this examples, I am taking a natural products. Look here. Of course, this I am discussed already, but this is the one is not discussed. Here you can observe that one is a ketone is there, another one is an ester is there. So ketone also is converted into alcohol. An ester, initially ester is converted into aldehyde and the aldehyde further reduced with the lithium aluminum hydride and giving rise to alcohol. So that's what a more particular what you can say that this is a functional group, this is alpha, this is beta. A beta keto ester gives rise to beta hydroxy alcohols. So diols, beta hydroxy alcohol are the product. Otherwise 1,3-diol is the product. Again here also you can observe a carbamate NCO2 NCO2H is called carbamic acid. NCO2 tertiary butyl, it's a carbamate is called carbamate. So carbamate ketones. So here the carbamate does not affect with the lithium aluminum hydride, but lithium aluminum hydride converts a ketone into alcohol. I will also take a quite interesting sample examples. More particularly, I think you are aware about the chair form and cis form, stereochemistry of cyclohexane, more particularly a disubstituted cyclohexane. So these examples are important as far as examination is concerned. So this is called 4-tertiary butyl cyclohexanone. So 4-tertiary cyclobutyl-hexanone, more particularly I am taking a chair form. So in this chair form, the tertiary butyl group is occupies a equatorial position. So equatorial position of bulky group is the stable one. So here also equatorial position of bulky group. Here the bulky group is what is tertiary butyl 1. So, but what is the reacting species? A carbonyl compound is the reactive species. And here lithium aluminum hydride, so can come from here. I think you are aware about the prochiral. So prochiral molecule. This is a prochiral molecule. Hydride can come from this side as well as this side. And here the formation is important. If the hydride is coming from here, so then what is called as equatorial hydroxy is formed. So you know that bulky groups occupies a equatorial position. Such compounds are more stable because of the interaction. Okay, steric hindrance. So here less this is a bulky group occupies equatorial position. This is a bulky group occupies equatorial position. That is the reason this product is formed in a 90% yield. So whereas the other one, so here other one, suppose a hydride is coming from this side, then it forms a what is called as axial hydroxy. So this is only forms a 10% yield. So here I am talking about the 1,3 interactions. 1, 2, 3, 1, 2, 3. So 1,3 diaxial interaction. So 1,3 diaxial interaction means it's a steric hindrance. So in this case, 1,3 disubstituted cyclohexanone, lithium aluminum hydride also can attack from here, and it can attack from this side. So in this case, the equatorial hydroxy, that means hydride coming from here, it's a less percentage, 45%. The hydride coming from here, it's more percentage, that is 55% is the one. And in this name of this compound is called benzophenone. Benzophenone is converted into benzhydral. Lithium aluminum hydride, it will act as a source of hydride and will attack electron deficient carbon and giving rise to benzhydral. This is a this also a solid, this also a solid. So this is about what is called as one particular concept, more particularly lithium aluminum hydride. It's a reducing agent. It can be prepared by the reaction of lithium hydride and lithium aluminum. And since it is a hygroscopic in nature, these reactions are carried out in inert atmosphere, and this can act as a source of hydride, and this hydride can reduce as a carbonyl compound into alcohols. So general mechanism I am explained. This is about the general mechanism, and these are the few examples. Few examples means alpha beta unsaturated ketones or carbonyl compounds converted into alcohols. So here, if there is a temperature dependent, if the reaction is carried out at higher temperature, lithium aluminum hydride, it is possible to reduce a double bond into a single bond. So that's what you need to remember. I'm also discussed about the few example naturally occurring compounds. These are naturally occurring. So you can observe that a ketone as well as ester also reduced to alcohol. So in the case of carbamates, a ketone is reduced to alcohol. So in the case of what is called as a substituted cyclohexanone, so more stable product is the obtained. More stable, how you will come to know that? The bulky groups occupies a equatorial position. Ones are called more stable one. So in 1,3 diaxial interactions, so this compound, axial equatorial hydroxy is 45%, axial hydroxy is 55%. So benzophenone is converted into benzhydral. So this is about what is called as a reduction. More particularly, I took only the substrates of carbonyl compounds, but I did not touch the other substrates. Maybe in the next class, I will be taking a few more examples of reduction of lithium aluminum hydride. So tell me, is there any doubt up to this? Hello?
No, sir.
Okay. So if there is no doubt means maybe I can stop at this stage. Maybe in the next class I will continue the reduction. And you all remember that tomorrow is the industrial visit. All should be present. Okay. Maybe all of you come to the college by 9:15 itself.